Hello, this is Joe Neville and welcome to this video about Aruba, AOS-CX, VXLAN and MTU. This is part of my ongoing series about VXLAN, and if you watched the previous video you might be expecting a different subject, but what's happened in the meantime is that I've seen a couple of queries come in about VXLAN and what that can do to a packet and the implications for the network and the MTU size. As we've previously seen, VXLAN encapsulation makes the packets bigger, and that can cause issues on the network, which we'll be going into. Spoiler alert, the encapsulation may make the frames too big to be sent with the default configuration in your underlay network. So it's good to be cognizant of that and work out a suitable MTU for your underlay. That's what we'll be going into, but we'll look at the details about what's really going on here. Now, the VXLAN header is just 8 bytes, and here it is on screen. But I was talking to a colleague and he was saying about the 50 byte increase to a packet size when encapsulated by VXLAN. And that made me pause and think, okay, so if the header's 8 bytes, what are these 50 bytes made up of? So let's drill into that. Now, the increase of frame size of 50 bytes, and that is because you're not just adding the VXLAN header, are you? Now, let me bring my laser pointer up. So we've got the VXLAN header here with your 8 bytes, but we're also adding some additional headers, so the outer headers need to be added as well. So we've got the UDP header as well of 8 bytes. We've got an outer V4 header of 20 bytes, and then you've got an outer Ethernet header of 14 bytes. You add all of those together and that makes up your 50 bytes. Now you may have an 802.1q tag as well, so it will add 54. Now I'll go into that later in the video, okay, because for various reasons. I don't want to get tangled up in that one just now. But the approach we're taking is that we're adding 50 bytes. Now, if you were previously sending at the unencapsulated maximum of an MTU of 1500 bytes, then adding that extra 50 could mean that it exceeds the maximum transmission unit of an interface and the packet will be dropped. So the encapsulated frames exceeding the MTU, that can cause issues as the traffic traverses the underlay network. So just diving into MTU and what that actually means for CX. So it's the maximum transmission unit is what you can send, but what is counted in here is not the Ethernet header. It's actually the unit that is going to be encapsulated by Ethernet. Okay, so what it is, this 1500 is made up of the outermost part of it is the V4 header. Okay, and then the rest of it, so all those other, the UDP and the VXLAN header, or if this is just a native packet, this is just like the data payload in here. Okay, so everything that the V4 header, of course, I'm just looking at V4 at the moment, we'll do V6 later. It's the encapsulated packet and the V4 header that makes up the transmission unit of 1500. So if you were to look in Wireshark and look at something that was flowing with the maximum MTU of 1500, what you would actually see is that it's larger by an Ethernet header and possibly by an Ethernet header plus an 802.1q tag, all right? So if you looked in Wireshark, you may see that the frame at layer 2 is actually 1514 or possibly 1518. But what's considered part of the transmission unit is just everything encapsulated by that Ethernet header. Okay, hope that makes sense. And to give you an example of the configuration of MTU on an Aruba AOS-CX device, here's a capture from a 6300. So MTU is set per interface. Here I've gone into the interface and there is the MTU command. So this is for layer 2 interfaces. So no routing would also be on this and it's switching traffic. There we've got the available values that go from 46 to over 9000 with the default of 1500. And just to reiterate that, if at this level the packet size is 1500, if you were then to sniff that in Wireshark, you would actually see that it was 1514 if there was no VLAN tag, or 1518 on the wire with a VLAN tag. And also, so this is the layer 2 with just MTU against the interface. There's also, for layer 3, there's IP MTU. So that's the IP payload. Here you can see that's configured under layer 3 interfaces with this IP MTU command, and that also defaults to 1500. Now I've got a show command here. So if you do a show interface, this is against the physical interface, so the layer 2. You'll see against that you've got the MTU of 1500. And you have some stats which are useful for that, because what you're looking for is errors and giants there. And what I've done in the next capture is I actually dropped the MTU so it was below the regular level. So I put it as 1400, and then I sent some traffic, and you can see I've got some errors there that have incremented, and they are listed as giants. So those would have been dropped. To illustrate what's going on with VXLAN encapsulation and MTU then, with the changing of the packet sizes, I've created this series of diagrams, the basis of which is a 3-switch and 2-server network. The servers are Ubuntu servers, and they're acting as the client side. Then we've got 6300-1 acting as a vtemp. -2 is also a vtemp, and I've got this transit switch here which is acting as a layer 3 gateway with a VXLAN going between the two vtemps. Now if I do a ping, so this is the Linux ping off of this Ubuntu 1 over to Ubuntu 2 here, and I've set the ping size as 100. What's that actually made up of on the wire? So if you were to do a Wireshark capture of this packet as it's sent out of Ubuntu 1, what you would see is that the data section is 100, then you've got the ICMP header of 8, then you've got a V4 header of 20, and you've got the Ethernet header, so it's native, there's no tag, it's 142. Remember this part here, these 3 sections, these are the 3 sections which count against MTU with Aruba AOS-CX. Let's move forward then as it goes through the vtemp and is encapsulated. So with the encapsulation, we have the VXLAN header, the UDP, the new outer V4 header, and the Ethernet. So it bumps it up to 192 on the wire, and 178 being counted against the MTU. There's no VLAN tag across these links either. Okay, so that will then flow across. It will traverse the transit here, but the packet size stays the same. And then it will be decapsulated by -2, so we lose those outer headers, and it goes back to 142 on the wire. And then in reverse, encapsulated through the transit and decapsulated as the ICMP echo response returns back, and we get a successful ping. So in the previous example, there wasn't an issue that VXLAN encapsulation was adding 50 bytes because the packet size was small and was way below the MTU value of 1500 by default. But what if we send a larger payload? Now, 1472 is the maximum payload that you would normally be able to send on a V4 network without fragmentation and the default MTU settings. And this is how it's made up then, the packet. You've got the data payload of 1472, you've got the ICMP of 8, making 1480, add on the 20, you got 1500. So this is your MTU. But in this setup, because we are encapsulating, we've got all of those additional headers, the encapsulated Ethernet, VXLAN, UDP, IPv4, and this figure here, so the 1550, is obviously over the MTU of 1500. And what happens then? Well, we're exceeding the MTU and the packet gets dropped. Now, there's a few different ways to solve this problem, but let's refer to the VXLAN RFC because it speaks about this issue specifically and offers some advice. And here's the relevant snippet in the VXLAN RFC 7348, of course. Now, there's a lot in there, so let's step through this piece by piece. First of all, vtemps must not, so strongly worded, must not fragment VXLAN packets. They're there to switch and encapsulate the traffic. They're not going to perform any IP fragmentation for us. So it's not the vtemp's job to solve the problem of packets that are too big when they're encapsulated with VXLAN. Okay, it continues. Intermediate routers may fragment encapsulated VXLAN packets due to a larger frame size. So we may fragment VXLAN on routers that sit on the path in the underlay between the vtemps. Of course, the traffic is going to be IP traffic for them, so they can fragment that. But we move on to the next point, and this is really something to bear in mind. The destination vtemp may silently discard such VXLAN fragments. This is not good, and it specifically says it may silently discard, so we don't even get a warning. This isn't good, and it means that we don't want to, so we can't do any fragmentation on the encapsulating VTemp. We can on the intermediate routers, but then when it's on the receiving VTemp, it might just dump those fragments. So, and I think the conclusion that we can draw from that is that fragmentation and VXLAN is a bad thing. So how to solve it? Well, there's some suggestions here. And it says, to ensure end-to-end traffic delivery without fragmentation, it is recommended that the MTUs across the physical network infrastructure, so the underlay, be set to a value that accommodates the larger frame size due to encapsulation. So we're going up by 50 bytes, increase your MTU across your underlay by 50 bytes at least. Another technique that you may use is to use path MTU discovery. For that, you would need to ensure that ICMP is free to flow through the network, which is not always possible to guarantee that. So the first and the recommended approach is to up those MTUs. Okay, that's the RFC recommendations. Let's implement them in the lab. Here's my lab setup. So I've got the three 6300s, I've got the two VTemps here, and then I've got this transit switch, and the transit switch is just acting at layer 2. And then we've got the two Ubuntu servers here, which act as the customer side. And if we want to send a ping, which is the maximum that we can get through with VXLAN encapsulation, the size is 1422. Okay, and the way that we work that out is that when it's encapsulated, the 1422 has the ICMP, the V4 header, the Ethernet header, the VXLAN, the UDP, and then the outer V4 header, which makes 1500 bytes. So that is matching the MTU settings on our devices, and that will flow through the network for us. Now, what if we wanted to send a ping with the previous maximum payload? And that would have been, so the non-VXLAN implementation, we would have been able to send payloads without fragmentation of 1472. Add in those additional headers, and that comes to a VXLAN encapsulated packet of 1550. So that's obviously going to get dropped by default. So what we're going to do in the lab is we're going to configure this underlay network to allow this previous maximum to flow. And this is quite interesting because we've got these two VTemps, which have got two settings. So we've got to set the MTU and the IP MTU. So layer 2 and layer 3 interfaces need to be incremented. I'm going to put it up to 1600, and the same over on the second VTemp there. And then, but for the transit switch, the interfaces on the transit switch, because it's just layer 2, we can just set the MTU, so not the IP MTU. Okay, let's get onto the boxes then. Okay, here I've SSH'd into the devices in my lab. So over on the right, we've got the 6300-1, -2, and -3. And over on the left, actually, I'm not logging into UB2, don't really need to. I've got two SSH sessions into UB1, and the reason for that is that I'm going to do the pings from here. I'm going to run a TCP dump on the bottom one so you can see the size of the packets. Okay, so starting with -1, if I show you the config, there's no setting for MTU on there, okay? I haven't made any adjustments, so it's just the default for the IP MTU and the MTU. Now, if we look at, what is it? This is the interface that faces the transit. And there you can see MTU of 1500, okay? I should clear off these statistics as well. So to clear the statistics, let's go global, yep. Same deal on 2. Global, yes, please. And the same deal on 3. Clear in statistics, global. Okay, good stuff. Now to show you the configuration then, what we have is we've got a VXLAN interface, of course. We've got the source is local. Then we've got the peer as the remote, that's -2. And this config is reversed on -2. This source here is this VLAN here, and I've just got a /30 there. And on -3, I've got these two interfaces, which are, this one faces 6300-1, and I've even got descriptions on there. How lovely. Okay, so just acting at layer 2 there. Right, now over here, I'm going to run the ping. So the ping, let's start off simple. we do a size of 100, and I do a count of 1, and it's 172.18.2. I just went too fast. 172.18.1.2. Okay, and down here I'm going to do a TCP dump. So TCP dump and the the interface is, if I can remember this one, it's a bit awkward, and an ICMP. Okay, I think that should work. There we are. Okay, let's do a ping. Good. Right, so that's gone through, everything's working, and in the TCP dump you can see the length there. So 100 in the payload becomes at the ICMP level 108, and then at the V4 level 128. Okay, so this is the request and that's the reply there. Good. Right, now, so let's go and increment this to the maximum that we can send. So that is 1422. Go. Yes, that works. Right, so at the ICMP level, it is 1430. Then at the V4 level, it is 1450. And then we've got the VXLAN encapsulation headers that have been added. So we've got the Ethernet header of 14. We've got the VXLAN and the UDP of 8 bytes each. So we've got 14 plus 16, 30. Then we've got the V4 header as well, making it up to 1500. So this can flow through the network. But if we go one more, so there, okay. So that is not working, okay? And the reason is there you can see that we send it, but it's getting dropped in the network. Because we're going to be sending a packet when encapsulated, which is 1501. Now, there's multiple factors at play here because you've got the MTU and you've got the IP MTU. So MTU being for all of the traffic on the interface, but the IP MTU being for the IP traffic. A really simple way, so if I do that, a really simple way is to show this. Is on my transit, what I can do is I just go onto the interface that faces 6300-1, and I can drop that down to a low level. And if we go back to the ping that previously worked, it doesn't work now, okay? And you actually see that if I come out there and we'll do show int, and I know that it will be on this interface, we'll see there we've got an error, and it's a giant. So it's too big. The MTU is smaller than the packet that's come in, and it's been dropped by this -3 in the transit. Okay, so let's go back then. No MTU, so that will reset it, and I'll do clear those stats off. So there's the examples of the pings that can't get through. So let's do something to make sure that the pings can get through. And I want them to get through to the level that they would normally get if we didn't have VXLAN. So that will be 50 more 1472. Just to prove it, of course, it's not working. Right. So what we need to do is on this device, I'm going to go to the interface and set the MTU. I'm going to go much higher, so MTU 1600, and then on the layer 3 interface as well, I'm going to go IP MTU 1600. So show that configuration. There we are, 1600, and show run int VLAN 1 1600. Good. Right, now if I ping with this amount, and I haven't changed that, you'll see that the traffic will actually flow from here and it will hit this one. So let's send that. Okay, so I've sent one packet. If I do a show interface on that near side interface, again, look, we've got that error. So we know that the traffic is being sent by my first VTemp, but it's hitting the transit and it's failing. So what do I do now? Well, I will go to, and it's just the physical interfaces, so I'll go MTU 1600, and then this one as well, which faces -2 1600, and I believe, let's see if this works. Right, so this is -2, and I have no errors on there. But I haven't changed -2 yet. So we should be able to see the traffic going through the network. I'll send one. Okay, that has been sent. Let's try those stats again. And there we go. So the error is now hitting -2 on the interface that faces -3. Okay, so we know that the traffic, rather than having to set up multiple places to stiff in the network, we can see the error actually moving through the network in this way. So finally then, I have to change the MTU on the interface. So I'll go 1600 and it's interface VLAN 1, IP MTU 1500. And fingers crossed. Oh no, I've made a mistake there, haven't I? Okay, there we go. Right, and fingers crossed, it works. I'll send a few of those just to show off. And then you can see below. Okay, if we look at this below, you'll see that we've got, where is one of them? The echo request there. So the length is 1472 plus 8, 1480 plus 20. We've got an IPv4 packet of 1500 bytes. And there you've got the reply. So that is successful. We've implemented the recommendation from the RFC to increase the MTU size on the transit network. A quick recap then of what I was doing. I was sending a ping of 1472 from Ubuntu 1 over to Ubuntu 2. And on the first VTemp, I configured the MTU for the layer 2 interface. So that's 1/1/10 that faces this transit switch. And I also configured the IP MTU. I pushed that up to 1600 for the layer 3 interface, which services the underlay. That was just interface VLAN 1. You can't get these mixed up on the interfaces. You can only configure the MTU command under a layer 2 non-routing interface, and you can only configure IP MTU on a layer 3 interface. I also configured the same on the second VTemp, and for this transit switch, which is just acting at layer 2, I merely configured the MTU for the physical interfaces. If this was layer 3, then I would have to configure the MTU and the IP MTU. So let's have a look at some of the alternatives to solving this problem. We do get it sometimes where a service provider will say, for whatever reason, we can't configure the MTU. Now, for years, the RFC of VXLAN, and this is, I think it was 2014, has said the recommended approach is to configure the transit network, which I've done. But what are some of the alternatives if you get stuck? Here's some of the alternatives that I've heard then. So what you could do is you could manually reduce the server MTU. That's not great because you're sending less data per header because you've implemented VXLAN. So your networking decisions are having an impact in your wider IT environment. Also, it's a networking issue that you would have to speak to the people that manage the servers. In some organizations, this would be completely different teams. And it's like, well, you got made a networking design choice, and now the server admins have to make a change. Possibly an issue. So this is if you were to statically do that. The second alternative, which is mentioned in the RFC, is to rely on the path MTU. So the ICMP messages would go back to the source and say, reduce your MTU. So it's like automatically doing it. Not great, because a lot of the time ICMP messages won't flow. Like, you would have to guarantee that these messages could flow through the transit network, or you could have an issue. So this isn't a great one to rely upon. Small labs, absolutely fine, but in larger environments, not really something that you would want to consider as a first choice, I think. This is just recommendations. And then finally, an SD-WAN solution. So what you could do is you could put a dedicated box in the path after the encapsulation, which would deal with fragmentation. So that would be able to handle the fragmentation of the VXLAN packets to reduce it down, and then it would pick them up. One of the issues with I'll just show you a diagram of that. So your SD-WAN boxes here and here, dedicated along with all their other features, to allow traffic to flow through the network. So you're taking control of this. Obviously, you're adding extra pieces in there, and it's just a brief word on that. Some of my colleagues might want to pick up on this if they feel like I'm not really doing this justice, just putting it at the end as a possible solution. But If you recall, the issue with fragmentation is that the boxes may silently discard them if fragments arrive, but in this case, the SD-WAN boxes would fragment and defragment, so the vtemps would be unaware. They would have fully formed VXLAN packets. I think that's enough VXLAN and MTU for a single video. So we had a look at the encapsulation header, which is not just the 8 bytes of VXLAN, it's actually 50 bytes for IPv4. And some of the issues that increase in size for the frame can cause. We had a look at the RFC's recommendations, and then we jumped onto the network and configured some devices, upping the MTU to allow the traffic to flow to the levels that a normal IPv4 traffic would be able to. What was that ping? 1472 in the payload. And then finally, some alternatives. Every piece of documentation that I've looked at around this says, first approach, most recommended, is going to be to up the traffic in the transit network. But that's on paper. In the real world, sometimes that is not an option. Okay, that's it from me. My name is Jay Neville. Thank you very much for watching, and goodbye.